today we're going to take a look at integrals involving inverse trig functions. Now, I know many of you probably have forgotten a little bit about your trig functions, or rather inverse trig functions. We have been using trig functions, but not things like sine inverse or cosine inverse, the inverse or arc sine, arc cosine. We're going to be going over them a little bit as a review, and then we're going to do integration with them. Now, just to give you a perspective, like where we're headed by the end of this section today, by the end of the lesson, you're going to be able to integrate things like the following. Say the integral of, let's say, dx over, say, 10 plus x squared. Can you integrate this with what you know right now? Try u substitution, right? Let u be 10 plus x squared. What happens? You get a 2x dx, right? There is no x on the top. So this question cannot be done with u substitution. We need something else. And again, integration in a sense is a lot more complicated than differentiation, because every time there's a slight change in the problem, you've got to have a completely different method to solve it. So today we're going to go through a long journey. It may take us half an hour to get there, because I have to go back and review inverse trig functions. You know, yes, I could give you the formulas in 2 seconds, but then there is no understanding. So we're going to try to go through the journey to understand how to integrate something like this. So along the way, of course, we're going to learn other things as well, like how do you differentiate inverse trig functions, etc. But this is our ultimate goal, to be able to integrate things of this nature. So some quick review items. First of all, say that we have sine inverse of A. What does it represent? So just a reminder, the inverse trig functions represent an angle. Like in this case, I label it as theta. Sine inverse of A represents an angle theta. And if I write that, this means that sine of that angle is equal to A. In other words, if you apply sine to both sides of that first equality, if we apply sine to this side and sine to this side, sine and sine inverse cancel, and you end up saying A is equal to sine theta. Basically, that's what you have over here. Okay, so let's do some examples. But before I can do some examples, also a reminder about, this is important, the range of inverse trig functions. The range. Now, for example, when I say sine inverse of 1, this means give me the angle, and the angle must be in radians. That's the way these inverse trig functions are defined. Give me the angle in radians where sine of that angle is equal to 1. So give me one example. Where I'm trying to find out where is sine inverse equal to 1, and the answer should be in terms of radians. Based on this, the way that works is give me an angle whose sine is equal to 1 in this case. An angle whose sine is equal to 1. Pi over 2 is a good one, right? Sine of pi over 2 is 1. So, but could I also say that sine of, what is pi over 2 plus 2 pi? So pi over 2 is over here. If you go around the whole circle one more time, you're going to have like pi over 2 plus 2 pi, which is 4 pi over 2. So would it also be at 5 pi over 2? Is it still 1? It is, right? But when we say sine inverse of 1, you could not give me the answer of 5 pi over 2. Even though sine inverse is equal to 1 at 5 pi over 2. The reason for that is we have these restricted ranges for the inverse sine function. When you give me an answer for the sine inverse, it always has to be in that restricted domain, or for sine inverse is the range. So pi over 2 is an acceptable answer. This is acceptable. But 5 pi over 2 is not. Why is it not? Because it doesn't lie in this range. The answer you give me for sine inverse should always be between negative pi over 2 and pi over 2. This is what makes sine inverse a function. A function, when you give sine inverse of 1, it shouldn't give you 2 different answers. A function only gives you a unique output for every input. This is why they had to restrict the range of this sine inverse function. Okay, what about cosine inverse? The range there is restricted from 0 to pi. That means anytime you give me an answer for cosine inverse of something, it has to be between 0 and pi. And for tangent inverse, it's between negative pi over 2 and pi over 2. Now you might say, how did they come up with these? You know, why are they not all of them negative pi over 2 to pi over 2, for example, right? As a matter of fact, I'm going to fix something here. For tangent function, it should be open interval pi over 2 to pi over 2, because tangent at the endpoint is not even defined there. Okay, so why are they doing this? Why are they picking these ranges for these inverse functions? Well, think about it. So let's think about, first of all, the sine function. Okay, the sine function looks something like this, right? Okay, give me an interval where it assumes all possible y values, the sine function from -1 to 1. So, for example, over here, sine function is -1, right? Over here, sine function is 1. In this range from here to here, and this happens to be -pi over 2 to pi over 2, the sine function assumes all possible values, right? Anything from -1 to 1. So they could have said just as well, they could have said, instead of going from -pi over 2 to pi over 2, we're going to go from pi over 2 to, from here to here. From pi over 2 to pi, because over there also sine assumes all the values from -1 to 1, right? But it's just easier when you have 0 in an interval, and universally this has been accepted, so all math books have the same interval from -pi over 2 to pi over 2. So also the calculators are programmed this way. If you do sine inverse of 1, it's only going to give you pi over 2 as an answer. It's not going to give you 5 pi over 2 as an answer. But then we know, of course, there are other values where it can be equal to 1. Why did they pick cosine from 0 to pi? Look at the graph of the cosine function. Cosine function looks like this. So where would you choose it? So it assumes all values from 0 to 1. I'm sorry, from -1 to 1. So they happen to go from 0 to pi. Over the interval, does it assume every value from -1 to 1? It does, right? So they could have just as well gone from pi to 2 pi for the cosine function. But usually if an interval contains 0, it makes things easier in the future. So they pick that range for the cosine inverse function. Okay, now let's do some examples about inverse trig functions. So starting with sine inverse of 1. We already talked about that one, right? What is sine inverse of 1? It has to be, your answer must lie in this range, -pi over 2 to pi over 2. So we already talked about this one. This one is going to be pi over 2. Now, some of you might say, well, all those things we did in trigonometry, was it a waste? Like we learned, it's going to be 1 at pi over 2, at 5 pi over 2, things like that. Well, those are still true in trigonometry because you solve equations like this. Sine of x is equal to 1. There, x will have infinitely many solutions, pi over 2 plus or minus 2k pi. But if the question says simply, what is sine inverse of 1? Sine inverse is a function. It should only have one answer, and the answer is pi over 2. Okay? What about cosine inverse of 1? For which angle in 0 to pi interval is the cosine function equal to 1? 0. Now, could I have said 2 pi as the answer? No. Even though cosine 2 pi is 1, there should be only one answer, and that answer must come from that interval from 0 to pi. And luckily, if you ever put this into the calculator, it will give you the correct answer automatically for the cosine inverse. It's going to give you 0 for cosine inverse of 1. If you don't trust me, try it on the calculator. Make sure you're in radian mode for when you do these things, and it'll give you the right answers. Okay, what about tangent inverse of 1? For which angle in radians is the tangent function equal to 1? That's when sine and cosine are equal, right? When is that happening? At pi over 4, at 45 degrees. In other words, at pi over 4, tangent is going to be exactly 1. Therefore, tangent inverse of 1 is pi over 4. Okay, what about cosine inverse of 1/2? At which angle is the cosine function equal to 1/2? Cosine of 60 degrees is 1/2, right? And 60 degrees in radians is pi over 3. So the answer will be pi over 3, and it does lie in that range 0 to pi. We can accept this. What about sine inverse of 1/2? When is the sine function equal to 1/2? Sine of 30 degrees, in other words, pi over 6, right? Pi over 6. Okay, just a couple more practice, and then we go to something else. Tangent inverse of -1. Tangent inverse of -1. Now, the answer must be in this interval from -pi over 2 to pi over 2. Now, if you think about the tangent function, also on the unit circle, we know tangent of pi over 4 is 1, right? At pi over 4, tangent is going to be exactly 1 there. Now, going from here to here is like going 0 to pi over 2, right? And going from here to here is kind of like going from 0 to negative pi over 2. So at which angle there do you think the tangent function will be equal to negative 1? At negative pi over 4, right? So the answer will be negative pi over 4. And how do I know tangent is going to be negative in this quadrant? How do I know that tangent will be negative? Exactly. Basically, the x-axis is positive, x-axis, y-axis is negative, x-axis. Tangent is the ratio of y to x, right? So if one is positive, one is negative, tangent will be negative. So in this region, tangent will be negative. And could you have given the answer like this? Because negative pi over 4 can also be given as 2 pi minus pi over 4, right? This is like 8 pi. So basically 7 pi over 4. Could you have given me the answer as 7 pi over 4? No, why not? Because it doesn't lie in this range, right? The answer should be from negative pi over 2 to pi over 2. So here the answer will be negative pi over 4. Okay, finally think about cosine inverse of negative a half. What would that be? Cosine inverse of negative a half. First, do we know where cosine inverse of 1/2 is? We already did that, right? Cosine inverse of 1/2 is pi over 3. Say over here is pi over 3. Which quadrant do you want to be in right now? Cosine has to be negative, and your answer should be between 0 and pi. So it's got to be in this quadrant, right? So in this quadrant, something with a reference angle of pi over 3 is what we want, basically. We want this angle to be pi over 3. So what angle would that be overall? Pi minus pi over 3, right? Because you want this angle here to be pi over 3. So if you want the original angle, that would be pi minus pi over 3, which is 3 pi minus pi, which is 2 pi over 3. 2 pi over 3. Does it lie in the range that we're looking for the cosine? Yes, because the answer should be between 0 and pi, and this one indeed is between 0 and pi. Okay, so that was just some general reminders about inverse trig functions. Again, luckily the calculator works the right way, so if you ever want to check something on the calculator, it will work fine. Now let's do something a little bit more involved. Say tangent of secant inverse of y over 5. How do we simplify a quantity such as this? Tangent of secant inverse of y over 5. Since we don't even know what y is, we could not possibly use the calculator. So what we're going to do instead is we're going to do a little triangle. Anytime you have an inverse trig function, consider that being an angle. It represents an angle. Like, for example, cosine inverse of 1 was 0. It represents the angle of 0. Sine inverse of 1 was pi over 2. It represents the angle of pi over 2. Anytime you have an inverse trig function, it represents an angle. So mark it as such. This is a theta. We don't know what theta is right now, but it's an angle. So ultimately, what we really need to find then is we need to find tangent of that angle. What is tangent of theta? If we can find that, we're done. Okay. So to do this, we're going to do a little triangle. Mark one of the angles as theta. And here's what we know about theta. Theta is secant inverse of y over 5. What does this tell you about secant of theta? If you apply secant to both sides, what would you get? Secant and secant inverse, they will cancel each other, right? You will have, on the right-hand side, if you apply secant to this side and secant to this side, what do you get? On the left, you get secant theta, right? On the right, you get secant of secant inverse. They cancel each other, and you get y over 5. So this is an angle such that secant of this angle is y over 5. So on this triangle, how would you label the sides as y over 5? Secant, remember, the ratio is hypotenuse over what? Secant is hypotenuse over adjacent. So hypotenuse should be y, and adjacent should be 5. Well, you guys tell me, what's the third side then? Use the Pythagorean theorem. It should be the longer side squared minus the shorter side squared, right? hypotenuse squared minus the leg squared, basically. So then we have both sides of this triangle. Now look at what we're trying to determine here. What we're trying to determine is tangent of theta. From this triangle, can you tell me what tangent of theta is? Tangent is opposite over adjacent. For this triangle, what is opposite over adjacent? The square root of y squared minus 25 divided by what? Opposite over adjacent. Adjacent side is 5. So there we have it. This is our answer for this question. The question had some y's in it, so it's okay to leave the answer with y's as well. So tangent of secant inverse of y over 5 equals radical y squared minus 25 all over 5. Now I'm going to give you a few moments to do the next one. What is cosine of sine inverse of y? Cosine of sine inverse of y, and I'll give you a moment. I'll pause the recording. So we begin in a very similar way as the last problem, right? Anytime you have an inverse trig function, call that an angle such as theta. So in this case, since sine inverse of y is theta, what can you say about sine of theta? This is an angle whose sine is equal to y, right? Okay, now if we could just find cosine of theta, we would be done. And to help us with that, we'll do a little triangle. Label one of the angles as theta. Now you want sine of theta to be y over 1. So opposite over hypotenuse is sine, right? So opposite is y, hypotenuse is 1. And what about the remaining side? Square root of 1 minus y squared. Basically 1 squared is 1 minus y squared. Again, because we're solving for the shorter side, the leg. If you were solving for the hypotenuse, of course, you would add the other two side squares. Now, what are we looking for in this triangle? Are we looking for tangent, sine, cosine? What are we looking for? Cosine theta, based on a given question. And cosine is adjacent over hypotenuse, right? And in this case, adjacent over hypotenuse would be radical 1 minus y squared. And that is the answer for this question. Did everybody follow that? Any questions about that? So hopefully it's coming back to you. I hope you have seen this in trigonometry, because so far we've not done any differentiation, any integration. So these are still we are doing some review here. But next we're going to get into doing some calculus with the trig functions. First of all, let me state the 3 rules. Okay, the 3 rules for differentiating inverse trig functions. So please write these down. And then I'm going to prove the first one. I'm going to prove why the derivative of sine inverse is 1 over the square root of 1 minus x squared. In just a little bit, we're going to understand why this works. Something unusual here. The right-hand sides have no trig functions, right? Like when you differentiate sine, you get cosine. When you differentiate cosine, you get negative sine. Usually when you differentiate a trig function, you get another trigonometric function, right? So this is something unusual. You differentiate an inverse trig function. You might think maybe I'll get an inverse trig function in return, but no, you get something completely algebraic, something with no trig or inverse trig functions in it, something very unusual. The last one is the derivative of the secant inverse function, and 1 over the absolute value of x on the bottom times radical x squared minus 1. So here we have derivatives of 3 inverse trig functions, mainly sine inverse, tangent inverse, and secant inverse. And you might say, what about the other ones? It turns out that the other ones are very similar to these. It's just like negative 1 times the other, and they don't come up as often, so I'm not going to give you those. But the first 2 of those are by far the most commonly used ones, so I'm going to ask you to memorize the first 2. Secant inverse, I'm not going to ask you to memorize. If you need to, you can always go back and find it from a textbook or whatever, but the first 2 are very important. They'll come up a lot in Calc 2 and beyond, so please try to remember those. Now, where do these formulas come from? So just to show you an understanding of it, I'm going to prove the first one, derivative of sine inverse. If you like this part, you may want to just follow. You know, if you don't want to write this part, that's okay. We're going to do examples in just a little bit. This is just for your understanding. Why is the derivative of sine inverse as given? Now, typically, basically, if you don't know the derivative of something, like we don't know the derivative of sine inverse, but we know the derivative of the sine function, right? We will try to make some use of what we know. Okay, so here's how we begin. We say let y be equal to sine inverse. Okay, we're trying to find then what? The derivative of sine inverse will be dy dx. Would everybody agree with that so far? We're trying to, if y is equal to sine inverse, if this is y, then we can say that the question at hand is to find the derivative of y with respect to x. Would everybody agree with that? Okay. Now, if you don't know the derivative of sine inverse, but you know the derivative of sine, let's bring in the sine function. How would you suppose that we could bring in the sine function to this equation? What could we do to both sides? Apply the sine function to both sides, right? So because we know something about the sine function, we want to make use of that. So that's what we're going to do. Apply, go ahead and apply, let's see, on my next page, I'm going to go back over there. Okay, sorry about that. Okay, so we're going to apply the sine function to both sides. This is what we get. On the left-hand side, sine of y equals, on the right-hand side, sine of sine inverse of x. Of course, those cancel. So this is what we get. Sine of y is equal to x. Would everybody agree with that? Okay. Next step, let's differentiate, because we know how to differentiate sine, right? What is the derivative of sine y with respect to x? Think of it as like sine u. You're differentiating it with respect to x. It'll have a cosine in it, right? Cosine y, but cosine y times something. Good. This is like the chain rule. Cosine y times dy dx, because we are differentiating both sides with respect to x, and this is what we get. Cosine y times dy dx. And what about the derivative of x with respect to x? That's just 1, right? Derivative of x with respect to x is 1, okay? Now, what was our goal again? What is it that we're trying to determine here? We're trying to determine dy dx, correct? This is our goal. Okay, so if I'm trying to determine dy dx and I have this equation, guess what I should be solving for? Look at the green box. That's what we're trying to determine, right? Dy dx. And here I have an equation that has a dy dx in it, right? So let's solve for dy dx. That's what we want to know anyway, right? So solve for dy dx. Basically divide both sides by cosine y, and this is what you get. Dy dx equals 1 over cosine y. Technically, we're done. This is the derivative of the sine inverse function, but you know, there's a y in here, and the original question, like sine inverse of x, it was in terms of x, this is in terms of y. We've got to bring in the original variable back. And here's how we're going to do it. We're going to create a triangle. Since you know that y is equal to sine inverse of x, let's actually look at this one. Since we know that sine of y is equal to x, so do a triangle where the angle is y. The angle is y. And how would you label the size of this triangle? If sine of y is equal to x, what would you put on the opposite side? Sine of y is equal to x. Think of it as x over 1. Opposite should be x, and hypotenuse should be 1. What about the remaining side? The square root of 1 minus x squared. So in this triangle, can you tell me what is cosine y? Cosine y is adjacent over hypotenuse, which is square root of 1 minus x squared over 1, right? Now, isn't that what we need in here? We need to plug in cosine y, and we'll be done. So go ahead and plug that in. Go ahead and do 1 over cosine y, which is the square root of 1 minus x squared. And that will give us the final answer. 1 over that is equal to, so we determine dy dx is equal to 1 over radical 1 minus x squared. Was that the answer we were trying to prove? It was, right? Derivative of sine inverse equals 1 over the square root of 1 minus x squared. Now, I'm going to ask you to do the following for the next class. Can you prove the derivative of the tangent inverse of x? Okay, when we come back, you know, we might begin with that question. If I forget, remind me. You want to make sure you see that because you might see something like that on the test. So write down a note to yourself. Part of the homework, do the derivative of tangent inverse. It's going to be very, very similar. You do the triangle and everything. So do it and then remind me at the beginning of the next class. We're going to begin with going over that example. Okay, now that we have these rules, we can now do some examples. Okay, but before I go to the examples, I'd like to give you the generalized rules as well. The generalized rules are as follows. Instead of x, I have u naught. So the derivative of tangent inverse of u equals 1 over 1 plus u squared times du dx. What is the only difference between this and what we learned in the last page? Yes, Ryan? Basically here you have an extra du dx, right? In the last page, if I go back to the last page, I'm going to interrupt this for one moment. If you go back to the rules I gave you earlier, you see here was the rule for tangent inverse of x, right? It had 1 over 1 plus x squared, right? And what do we have now? We have 1 over 1 plus u squared times an extra thing here, du dx. Where did the du dx come from? From the chain rule. You multiply everything with the derivative of the inside. So this is the generalized rule for the tangent inverse function's derivative. And what about sine inverse derivative? Very much like what we just learned a moment ago, like we just said it was going to be 1 over root 1 minus x squared. But if you have a u, then you have an extra quantity here, which is du dx. That also comes from the chain rule. Okay, finally, we're ready to do some examples. Let's find the derivative of tangent inverse of x, first of all. This one is just memorize the formula and give it back to me. This one right here. You just have to remember what the formula says. What is the derivative of tangent inverse of x? If you like, flip back to your notes. We just learned this. 1 over 1 plus x squared. Now let's do this one. The derivative of tangent inverse of 2x. Now you have a u. Your u is 2x. So the rule says do 1 over 1 plus what? The entire quantity squared. So what is the 2x quantity squared? If you like, let me write it like this for now. 2x quantity squared, right? Times du dx, which is? Because here the derivative of x with respect to x would have been 1. So if you just have an x, it doesn't even show itself. But anything other than x, you got to remember to multiply it with the derivative of the inside by the chain rule. Because again, the first one you could do that, but it's just a 1, doesn't change anything. So for this one, what should I have? What is du dx? This is your u. 2. So the answer is, in simplified form, 2 divided by 1 plus 4x squared. Can you tell me the answer for the next one? Tangent inverse of e to the x. So it will be 1 over, the rule is 1 over 1 plus u squared, right? So what is u squared in this case? E to the x quantity squared, right? And what do I multiply this with? The derivative of e to the x, which is e to the x. And I can simplify. What is the power of a power? How do you simplify this? Power of a power, you multiply the powers, right? So this will be 1 over, e to the x over 1 plus e to the 2x. Because power of a power, you multiply them. And let's also do the last one. The derivative of sine inverse of x squared. Okay, what was the rule for sine inverse of x? 1 over the square root of 1 minus, normally it's x squared, but here we have a u, right? It's not just an x. So whatever that quantity is, that quantity is squared basically. So what is it going to be in this case? X squared to the second power, right? Which will be x to the fourth. And I should multiply this by what? The derivative of this, which is 2x. Of course, you could rewrite it as follows, as a single fraction. Okay. So far what we've done, to recap everything we've done so far, we have reviewed your inverse trig functions. We've learned the derivatives of the inverse trig functions, and we look at the proof of one of them. Okay? So now we're slowly edging towards the integrals involving trig functions, because once you know derivatives, integrals are just going to be the opposite process. Right? Okay. Let me go and erase that. Cover that. Okay. Let's now try to remember or try to figure out what the integrals are going to be. We just learned that derivative of sine inverse of x, for example. Let's just do those one at a time. We just learned that derivative of sine inverse of x was 1 over the square root of 1 minus x squared. So what do you think it is? The integral of 1 over the square root of 1 minus x squared. Give me a function whose derivative is this? Sine inverse of x, right? So the answer to this one would be sine inverse of x. You know, who would have thought such a thing? Because think about it. If you wanted to integrate this quantity with u substitution, let u be 1 minus x squared, you would need to have an x dx on the top, right? And there is no x dx. So this is one of those integrals that u substitution does not work. And somehow a very complicated function comes out as an answer, sine inverse of x. Again, who would have thought? But it works. And what about this one, the integral of dx over 1 plus x squared? Once again, can you do this one with u substitution? Like let u be 1 plus x squared? No, because there is no x dx on the top, right? U substitution doesn't work there. But we just learned a function whose derivative is 1 over 1 plus x squared. So which function is that? Inverse tangent. So the antiderivative of this quantity is tangent inverse of x. And again, this last one you do not have to memorize, but that one turns out to be secant inverse of, I believe, absolute value of x plus c. Again, the first two, I would ask you to memorize, but if you've already memorized the derivatives, the integrals are really a natural conclusion of those. So you really just know one or the other. It's just the other one is automatically comes from the other. Okay, now finally I'm going to give you one last set of formulas, and I promise there are no other formulas today because I know we did a lot of formulas. But these are going to be more general. When I say more general, instead of having a 1, you could have any number here, not just a 1, okay? So if you have any number, such as a, the number a, this is what the answer turns out to be. So if you have the integral of 1 over a squared minus x squared under a radical. Again, how does this differ from the previous? We had 1 minus x squared there, right? So there a was 1. But it doesn't have to be. It can be any number. Then the answer changes slightly. Then it becomes sine inverse of x over a. And if you are so inclined, you can differentiate the right-hand side, and you'll be able to show that that will give you the left-hand side. Okay, and finally, the antiderivative of a squared plus x squared in the denominator equals, the moment you see the sum of two squares on the bottom, think about the tangent inverse function. And the rule says if you have a instead of having a 1, if you have the number a, then it's going to be 1 over a times tangent inverse of x over a. I want you to notice a difference here. In tangent inverse, there's an extra coefficient, 1 over a up front. In sine inverse, you do not have that coefficient. Okay, this is not a typo. That's the way it works out. And again, if you are curious, why are these formulas so different? I would encourage you then to differentiate this right-hand side and show that you're going to get the left-hand side. And with what we've learned today, you should be able to do that exercise as an exercise. So from now on, I would say, you know, there's one more formula for secant inverse, but I'm not even going to give that to you. I don't ask you to memorize it. If you were just to memorize these two, I think that covers everything we've learned today. Because this, from here, you can say, okay, if a is 1, what is going to happen? If a is 1, you have integral of 1 minus x squared on the bottom, right? And on the right-hand side, you would have x over 1, which is sine inverse of x. So this is more general. If you know this one, of course, you know the answer when a is equal to 1, right? And also, if you know this one, if I say, what is the derivative of sine inverse? Well, it will be like 1 over the square root of 1 minus x squared. That pattern is also included in this formula. So these two are the most general ones. And if you can remember these, you'll know all the other ones. Okay, now we're going to do some examples with them. Starting with the integral from 0 to 1 of dx over 1 plus x squared. I believe this was pretty much the example I promised you would get to by the end of the class today, or sometime during the class today. Because this we could not do with our knowledge prior to today's lesson. We cannot do this with U substitution, right? It's, this one is from 0 to 1 for the first question. Yeah, the first example is from 0 to 1. The integral of dx over quantity 1 plus x squared. So the moment you look at something, the first thought should be, can I use U substitution? And can we? The answer is no. There is no x on the top. Okay. So then we have to say, okay, is there something else I can use? Oh, wasn't there one of those inverse trig functions? Which one? Inverse sine or inverse tangent? Which one do you think works here? The inverse tangent. Anytime you see sum of two squares on the bottom, think about inverse tangent. In this case, your a is 1. So this is going to be inverse tangent of x over 1. It's a simple inverse tangent of x, in other words, right? Because normal it's like 1 over the a, but a is 1. It doesn't show up itself. Okay, then plug in the constants 0 to 1. So we need to find out what is tangent inverse of 1 minus tangent inverse of 0. At which angle is the tangent function equal to 1? Luckily, we've already reviewed this one earlier, right? What angle was it? If you look at your notes on the first page of today's lesson, that's when sine and cosine are equal. Their ratio is 1, right? That happens at 45 degrees. In other words, at which radian measure? Pi over 4. So tangent inverse of 1 is pi over 4. This comes up a lot. It's good to remember this one. Minus, what about tangent inverse of 0? Well, you may remember the tangent function looks something like this. At 0, tangent inverse of 0 is 0, basically. So the final answer will be pi over 4. What about the next one? First question, what should be the antiderivative of 1 over the square root of 1 minus x squared? What is the antiderivative? Sine inverse of x over 1. In this case, it's just going to be x. Now, how did I know this was going to be sine inverse? First of all, I might first be inclined to use U substitution, but there is no x on the top, right? Anytime you have a square root on the bottom, difference of two squares, one has to be a number and one has to be a variable. And further, the first one should be a number. Like if you had x squared minus 1, you could not use this rule. Then you need something you're going to learn in Calc 2. It has to be exactly in this format, a number squared minus a variable squared. That's when you can use sine inverse, okay? And in this case, a is 1, so it's as if you're dividing by 1. Limits are from -1 to 1. So first I need to know what is sine inverse of 1, and then I'm going to need to know what is sine inverse of -1. So you can think of the unit circle, or you can think of the graph of the sine function. We've already done the first one. When is the sine function equal to 1? At which angle is the sine equal to 1? Basically over here, right? What angle is that? In radians pi over 2. Okay, now at which angle is the sine function equal to -1? Now some of you might say it might be 3 pi over 2, right? Because over here, sine will be -1. But can I accept 3 pi over 2 as an answer? No, it has to be in between negative pi over 2 to pi over 2 range. So go this way then. Negative pi over 2. And the answer is pi over 2 plus pi over 2, or 2 pi over 2, or simply pi. Could we check our answer to this one on the calculator? Certainly. One thing is, like, you could just do sine inverse of 1 on the calculator. It gives you a decimal answer. Now, sometimes I say give me an exact result because I want you to know this. But yet you can check your answer to sine inverse of 1. Do it on the calculator. What are you getting as a decimal there? Could you do that, please? What is sine inverse of 1? And hopefully you're in radian mode. 1.57. And what is pi over 2? Like 3.14 over 2, it's going to be the same thing. Okay, so it's giving it the answer in decimal, okay? Also, you could do function integration. You can check the whole question from the beginning to the end. Enter the function 1 over 1, radical 1 minus x squared, comma x, comma the limits, and also then you can check the final answer to see if that came out to be correctly. Okay, a couple more examples, a few more. But these are pretty quick if you know your formulas. At a glance, let me just show you one at a time here. So let's just go one at a time. At a glance, do you think this can be done with U substitution? No. Do you think you're going to need tangent inverse or sine inverse? Sine inverse. What is our A here? 16 is A squared. So what is A itself? A is 4. A is the square root of 16. The formula says you need sine inverse of x over A. And what is A? 4. So the answer is sine inverse of x over 4 plus c. Any questions on that one? There was no 1/3 or 1/4 in the sine inverse formula. Only the tangent inverse has that extra coefficient. Okay, for this one, can you do it with u sub? No. What is A here? 3. Which function are we going to need? The tangent inverse. But remember, there's an extra coefficient here, which should be 1 over A times tangent inverse of what? The rule says x over A. In this case, it's going to be x over 3 plus c. Any questions on that one? Because addition is commutative, this could appear like this, or don't be surprised if it appears like this, x squared plus 9. As long as you have the sum of two squares on the bottom, one has the variable, one has a constant, you can use tangent inverse function. But for the sine inverse, it has to be in that specific order because there's a minus in the middle, okay? Okay, let's take a look at the next one. Again, if you know your formulas, these are really easy. Okay, for this question, what will be our A? Good, it will be the square root of 7 because 7 represents A squared. So for this question, A is the square root of 7. So could somebody tell me the answer from the beginning to the end? Yes, Joey, 1 over root 7 times inverse tangent of exactly x over root 7. And by the way, some books, instead of tangent inverse, they use this notation, arctangent. It's the same thing. Tangent to the minus 1 or arctangent is the same thing. But this is what tangent inverse is not. Unfortunately, mathematicians chose a bad notation. When they chose tangent inverse of, let's say, 1, this does not mean 1 over the tangent of 1 or something like that, right? It just means the angle whose tangent is 1 is pi over 4, right? But it doesn't mean this. It's just they chose this bad notation. I don't know why they did that. Later on, to compensate for that, they said, oh, we don't like that notation because some people will think that's 1 over something from algebra. So they said, well, maybe we should use arctangent so to eliminate that confusion. But I think our book still uses, and many books still use this tangent to the minus 1 notation to represent tan inverse. Okay, this question here, could you use arctangent for it? No. What should we use for this one? U substitution. There's an x on the top, so let u be equal to x squared plus 7 Then du is 2x dx. So we come up here. What should I have for x dx? Right, from here you can see that x dx is the same as du over 2. And I put the du inside over 2 outside, divided by the bottom, x squared plus 7, which is now going to be called what? U. So we've seen this integral last time. This is natural log of u. In other words, natural log of x squared plus 7. Okay, I think I have like 1 or 2 examples left. I really want to give you like 15 minutes if I can for group activities today. So let's see if we can do the following 2 examples. Don't worry about the top one, please. I want you to worry about this one. This one is a little bit different than the other ones we've been doing. You know, there are 2 ways to do this question. One of them would be you need to put this in the same exact format as a good tangent inverse question. What is an extra factor here? That 2 doesn't make it look like a real, you know, arctangent problem. But you could try to factor out a 2 from both of them. You could say, I can write this as if I factor out a 2 from both of them, what will be the first one? 9 over 2, right? Because when you multiply, you want to get back the 9, right? What will be the second one? X squared, because when you multiply, you want to get back to 2x squared. So now it looks more like a standardized arctangent, except that that 1/2, I'm going to take it outside of everything. So now this looks more like a number squared plus x squared. Can I use arctangent right now? Or inverse tangent, same thing. But let me ask you guys, what is going to be my a here? Remember, this number represents a squared. It'll be 3 over the square root of 2. Would everyone agree with that? Take the square root of the top and the square root of the bottom. Okay, so the 1/2 came from that problem, so I'm keeping that. Who can tell me the rest? First thing you want is 1 over a, right, which is, right, basically turn upside down, root 2 over 3, right? That's 1 over a, correct? Okay, then I'm going to need tangent inverse of what? X over a, x over a, and that's like division by 3 over root 2, right? But there's another way to write that. How could you rewrite that? X root 2, or root 2x divided by 3, because you can just flip it and multiply with the top, of course. So I think that's the way you would normally see it in a book, so I'm going to rewrite it that way. This is the same as, combine all the numbers up front, root 2 over 6 times tan inverse of root 2x over 3 plus c. And the other way to do this involves u sub, but I think I'm just going to show you one way to do it for now. Later, maybe I'll introduce one more way. And the last example, before I go to it, any questions on this one we just did? Any questions? Yes. Right, the first step was to take out a 2 from the denominator, and then I also factored it outside of the integral sign. So now that was basically just sitting all the way outside of everything, the 1/2. And later, exactly, it was distributed with the remaining constants. Okay, the last question, of course, is probably the most challenging. You got something here that doesn't look like an inverse tangent. You got extra x term in there. X squared minus 6x plus 10 in the denominator. Okay, first of all, I'm going to forget about the limits. I'm going to factor out the 2. And for the bottom, I need to rewrite this. I'm going to leave some space. Some of you may see where I'm headed here. I left some space there. Guess what I'm going to be doing? Complete the square. Remember that from college algebra? Complete to a perfect square. You add and subtract something. What do you add and subtract? I'll give you the little rule there. It's like if you have a bx in the middle, so you basically take half of your middle term coefficient, you square it. You're going to add and subtract this number. What is half of negative 6? Negative 3. Square it. Square it. You get 9, right? So we're going to add and subtract a 9 then. Add a 9 and subtract a 9. If you do this, you are guaranteed to have a perfect square in the first 3 terms. These first 3 terms we're going to turn out to be automatically into a perfect square. And you can always achieve this by adding b over 2 squared, and b is your middle coefficient there. That is the perfect square of what, by the way? This is the perfect square of x minus 3. And what are we left with over here? Plus 1. Now does it look like arctangent? You don't have x squared, but you have x minus 3 squared. Close enough. You could do a u sub here, like let u be x minus 3, but you can skip that because du will be equal to dx. When that happens, you can skip the u sub and just go to the answer. The answer is, okay, what is my a here? X minus 3 is my variable. And what is my constant, the a? The square root of 1, which is 1. So what you want here is 1 over a, which is just 1. Tangent inverse of, instead of x, we have x minus 3 though. So x minus 3 over 1, or itself. In other words, just write it clean like this. Tangent inverse of x minus 3. And we had limits, right? 2 to 4, is that right? Okay, plug the upper limit in. Minus 4 minus 3 should be a 1. Minus, plug the lower limit in. And we've already done this one. What was tangent inverse of 1? At which angle sine and cosine are equal and the ratio is 1? Pi over 4. I told you guys this is going to come up a lot. It really will be coming up a lot. And then tangent inverse of negative 1? Negative pi over 4. So we get a plus in the middle, or 2 pi over 4, or pi over 2. So 2 times pi over 2. I think we're going to get pi. Did I do that correctly? Let me just double check. Pi over 4 plus pi over 4 is 2 pi over 4. And there was an extra 2 on the top. So we get 4 pi over 4, or just pi.